Welcome back to the workshop. We want to continue on taking a look at section 3 of the appendix. For this example, we don't actually have a new method that we are presenting, but what we have is a proof of a biconditional. For a biconditional, we're looking at two implications or two conditional statements. And so to prove a biconditional, right, a biconditional is true when both of the individual conditionals are true. So we just need to show that each of the individual conditionals are true. So the implication, both directions, we need to show those are true, and that's it. Okay. So let's take a look at this example. Again, a proof of a biconditional requires that we show the forward direction is true. P implies Q, and we need to show that the reverse is true. Q implies P. Okay, so these are the notations that we'll use to denote which direction we're proving as we go through the proof. All right, so let's consider this example. Let P be a prime integer and B and C any positive integers. Prove that P divides the product of BC if and only if P divides B or P divides C. So if we were to take a look at a really quick example, if we were to consider the prime number 7, okay, so if we know that 7 divides, let's say, let's see here, we could go with 42. Let's see, is that what I want? Yeah, that'll work. Right, and 42 is equal to, we could say this is 2 times 21. That would be fine. So 7 divides 2 times 21. Excellent. So if 7 divides 42, and 42 is 2 times 21, we can clearly see that 7 divides 21. Excellent. And that's all that this is saying. If P divides BC, then P divides B or P divides C. And of course, if we were to build it up the other way, notice that 7 divides 14. So 7 divides any multiple of 14. Let's say 4 times 14. See, 4 times 10 would be 40, 56. There we go. Cool. All right. So forward direction, reverse direction. So in this case, we're letting P be any prime integer. B and C are any positive integers. So for this proof, we begin by letting P be a prime integer and B and C any positive integers. Excellent. So that's what we begin with, right? Those are just the setup. Those are some basic assumptions before we get to the actual implication. So now if I want to prove the forward direction, that is, if P divides the product, then P divides B or P divides C. Proving this direction is a little bit lengthy. It takes a little bit of time to get through it. It'll be okay. It makes sense. We just have to break things down a little ways. So assume assume the premise or the hypothesis. So for the forward direction, the premise is P divides the product. So assume P divides BC. Excellent. Now, P is prime. So what I want to do is I want to write B and C as products of primes. And we can do that. It's the fundamental theorem of algebra, the fundamental theorem of arithmetic actually allows us to do that. So by the fundamental theorem of arithmetic, we have every number can be written as a product of primes. So B we can write as P1 times P2 times P3 all the way up to times Pn for some n, for some integer n. And we can write C as Q1 times Q2 all the way up to Q. Now we don't know how many there are here, and certainly there may not be the same number of primes, so we'll use a different letter for all the way up to Qm for some m that is an integer, where, right, we want it to be products of primes, so where Pi and Qi are primes. Pi and Qi are prime for, let's see here, we have 1 less than or equal to I less than or equal to n. So for I values from 1 to n, and for Q values between 1, Pi and, sorry, Qj. I want to use different indices here, Pi and Qj. So I runs from 1 to n, j runs from 1 to n. There we go. So we're saying all of these are prime and all of these are prime. Pi and Qi are prime for I from 1 to n and j from 1 to n, because the p's go from 1 to n and the q's go from 1 to n. Simple as that. All right, hence B times C is equal to P1 times P2 times all the way up to Pn times Q1 times Q2 times all the way up to Qn. All right. Since P divides BC, right, I can't break this down anymore. Since P divides BC, we have that BC is equal to P times something. Since P divides BC and P is prime, we must have that P is equal to Pi for some I in the set of numbers from 1 all the way up to n, or P is equal to Qj for some j in the numbers from 1 to n. So since P divides BC, we can write BC as P times something. So BC, right, which is going to be P times K for some integer K. And we know this is true because P divides BC. So since we have that, P must be one of these numbers over here. So it's either one of these P's or it's one of those Q's. If it's one of the P's, then P divides B. Then P divides B. If it's one of the Q's, then P divides Q. Okay, and that's what we wanted to show. If P divides the product, then P divides one of the two of them. So P must be one of these or P must be one of those. and we essentially have what we need. Okay, so this gives us two cases. So case one, if P equals Pi for some I in the set of numbers 1 through n. I don't know which one it is for one of these. I is one of those, telling us that P is one of these P values. So if P is one of these, then let's see here, then B is equal to P1 times P2 times all the way up to P sub I minus 1. Pi is actually P, and then P sub I plus 1 all the way up to P sub n. That is, B can be written as P times something, and P divides B. So the other case is that if P is equal to Qj for some j in the numbers 1 through m, so we're saying that P has to be one of these numbers. It's either going to be one of these P values or it's going to be one of these Q values. If it's one of the P values, it's going to be one of them. I don't know which one. P1, P2, P3, I don't know. Pi. We'll call it I. What is I? Well, it could be any of 1, 2, 3, 4, all the way up to n. So we have that. If it's not P, then it's Q. Which Q? I don't know. It could be 1, 2, 3, 4, all the way up to n. I don't know. So it's Q sub j, where j is one of those numbers 1 through n. All right, excellent. So similarly, we can say then C would be equal to Q1 times Q2 times all the way up to Q sub j minus 1. I don't know what j is. It could be 1. Doesn't really matter. Times P, because Qj is P. That's what we're saying here. Times Q sub j plus 1 all the way up to times Q sub n. And we have C is P times something, so P divides C. Now, I don't know which of these cases it is, but it is one of them. And in either, when we bring them together, we have that P divides B or P divides C. Thus, if P divides BC, then P divides B, or P divides C. Excellent. So that takes care of the forward direction. Now we want to take a look at the reverse direction, which is a bit shorter, fortunately, because we have not a lot of room left. So the other direction, we want to assume that P divides C. I'll actually go B first, alphabetical order. Assume that P divides B or P divides C. All right. Does it matter which one it is? No, because as soon as it's one of them, then we know it divides the product. So since it doesn't matter, we can actually use this idea of just making it very general. So we can say, without loss of generality, we can just let it be one of them. We'll choose one of them. Let's let it be B. Okay, so we say, since it doesn't matter which one it is, the following work looks exactly the same. So without loss of generality, assume P divides B. Excellent. Then that gives us that B is equal to PK for some integer k. And that BC is equal to P times KC for KC in integer as well. Hence, P divides BC. All right, we have a little bit of room for our conclusion. We have two conclusions yet. We need to conclude the reverse direction here. So thus, if P divides B, or P divides C, then P divides BC. So that's the conclusion to the reverse direction. And now we can give the conclusion to the entire proof, which is the if and only if statement. Therefore, let's see here, P divides BC if and only if P divides B or P divides C. And that's it. Excellent. And that's it. So that was kind of long, but the main thing that you want to take away from that, even if you didn't follow every step in there, that's okay. The main thing right now is that for a proof of a biconditional, we have to recognize that we have to prove the forward direction and the reverse direction. Now, if you're watching this video because you're my student, I want you to know that when I'm looking at your proofs, I'm going to be looking for the same sort of structure in your proofs. So you should, when you're proving a biconditional, you should denote that you're proving the forward direction, and you should denote that you're proving the reverse direction. If you want to write it a little bit differently, that's okay, but you should be very clear about what exactly you're doing in these proofs. Especially, again, if you're new to proofs, if you're still developing this idea and developing your techniques, you need to be very, very clear with the presentation of your work, okay? Ideally, you'd want to present your work in such a way that someone else who wasn't very strong at proofs would be able to read and follow your work. That is, they could understand it, okay? So I might be able to read and figure out what you're trying to say, but that's not the goal. The goal is for you to be able to present your work so it can be easily read and understood without having to have someone figure it out. Okay, so that's the goal here. Again, this example, it might take you a couple of read-throughs. Hopefully I explained it well, but this is certainly more detailed than you might see in the proof written up by a text, okay? But that's all that I had for this video. So we've got one more video on proof methods, which is much, much shorter. So I'll see you guys back in the workshop very shortly.